Today's topic is going to be statistical assumptions. They're associated with most of the variety of tests that we're going to talk about in this course. So one comment regarding assumptions. We have data. We collect data. And generally people just take that data and they go ahead and they run statistical tests on that data. The problem is that every statistical test has some type of assumption associated with that test. Well, if you ignore those assumptions, it is very likely that any statistical result you have from that test are going to be invalid. So we have to be able to figure out what those violations of assumptions do to the test that we're going to be running, and if that test is even appropriate to be running after you find out what kind of data you actually truly have. So that's really why we're focusing on statistical assumptions this week. Is we're going to start to see that a lot of the tests have normality, homogeneous variances assumptions. We're going to talk about those, and that's really the first place you should start. When we get into very specific tests such as multiple regression or logistic regression or the ANOVA, we're going to talk about assumptions that are very specific to each one of those tests that we also have to verify. Generally, for any type of parametric test, we have to have normally distributed data. We're going to talk about what that looks like here in a minute. Our variances have to be similar. We have to have some type of interval or ratio data. Again, for parametric data, we cannot have categorical data. If you have categorical data, you must run a non-parametric test. So really the only difference between parametric and non-parametric is non-parametric, it doesn't meet the parametric data assumptions. And then the last parametric data assumption that we have to have is we have to have independent data for most of the test. Independent data means you have two manipulations, or one manipulation, a before and an after condition, so two conditions, and you have different people running in each of those two conditions. If you have the same people in both of those conditions, then you do not have independent data, and you have to use a very specific different type of a test. All right, so how do we figure out whether or not we have normal data? We're always going to assume our sampling distribution is normal. We really only need to worry about this when we have small data sets. If we have small data sets, we may or may not have normal data. Now, traditionally, the central limit theorem says the larger the data set you have, the closer you get to normal data. And there are some that says, well, a large sample of data points over 30, tend to be more normal. Well, again, that's more of an objective description, and we really want to say, let's look at the data and see if it is normal, because nobody really knows where the point of, we can be absolutely sure it's normal because we have such a huge sample versus a sample that is just adequate to make it normal. There's not a particular number there, so regardless of how large our data sample set is, we should also check for normality. 4 different ways to do this. We're going to go over each one of these. I lied. Frequency distribution, we've already talked about that. That's the histogram. And you can look at the histogram and compare it with the normal diagram and see if it looks normal. The next is our probability plot. And SPSS will do this for you. Again, it will plot the cumulative probability of one variable with the cumulative probability of a particular distribution, such as a normal distribution. For normal, that distribution is going to have a diagonal line. And if the data points fall on that diagonal line, then the data is visually normal. And that probability plot will show any very small deviation from that line. There's also the quartile plot, very similar to the PP plot. The results look very much the same, except here we're just plotting the quartiles instead of each plot or each data point. Here's an example of the probability plots. Obviously on the left, you can hardly even see the line, the diagonal line that is there, but indeed it is there. All the data points just cover up that line. So that would be normal data. Now on the right, you can see that that really does not look like normal data. You can clearly see the diagonal line. So in this case, we have some fairly decent deviations from normality, and we would not be comfortable saying that that is normal data in any sense of the imagination. So now we would have a problem. We have to figure out what to do with that data now that we know that we don't have normal data. But we'll get to that in a little bit as well. But that's what the probability plots look like. Here's a quartile plot. And again, generally has fewer data points. And you're probably, as engineers, saying, boy, both the frequency histogram and the probability plot and the quartile plot is all very subjective. Yes, it is. And we're going to talk about why it's not good to run multiple tests, because we do have tests that we could run, but it's not good to run tests on the same data over and over and over again. So because of that, we don't want to waste running a test on normality. We're going to look at it subjectively. So here, on the left, we do have some deviations from normality, but the vast majority of the data set is pretty much normal. So you have to decide what you're comfortable with, and there's more than one way to look at this. You can start to look at these data points a little bit if you're concerned about those, and look at the z-score. Here, this is really kind of getting far away from the normality curve. So we might want to consider that not normal. Other things that you can do is you can look at skewness and kurtosis. SPSS will print out information for you if you ask for the skewness and kurtosis, a little checkbox. And you can get that information. And if you take the skewness and you divide it by the standard error of the skewness, you can get a z-score value for that. And here are the z-scores, right? Just skewness divided by the standard error and the kurtosis divided by the standard error. Now, you should probably have values less than 1.96. You have a relatively small sample, or less than 2.58. Anything greater than those would be non-normal points or non-normal data set. Now, the problem is, with a very large sample, we can have very small standard errors, and that's going to lead to major normality distributions. So the larger the sample you get, the more potential you're going to have absolute values of your z-score for skewness and kurtosis greater than the limits. And that's why when you have very, very large samples, you should really just use the shape of the distribution and look at the probability or the quartile plots. Now the test, here we go, we have issues when we have running tests on data. We do not want to bias any future statistical test. We'll get to the Bonafroni correction factor later when we talk about the t-test. But what happens is when you run multiple tests on the same data set, if you want only a 5% error, running multiple tests is going to automatically give you much greater than a 5% error. So if we want to maintain a 5% error, we should only run one test on our database. Therefore, we don't want to waste the test in normality. But we're just going over the test just to make sure that you understand that there are tests that you could run. And we're going to kind of go through a few of those. So the two tests, the Kolmogorov-Smirnov and the Shapiro-Wilk, both of them do the exact same thing. They compare the data to the normal distribution, and a p-value greater than 0.05 tells you that your distribution is normal. Anything less than 0.05 means you do not have normal data. Now the two tests are very slightly different. The Shapiro-Wilk tends to be a little bit more powerful than the Kolmogorov-Smirnov. However, it can only be used for the normal distribution. And that's really the advantage of the Kolmogorov-Smirnov is there are various subdisciplines within civil engineering that you don't want to use the normal distribution. You might want to use the Poisson distribution or the log normal, and you can go ahead and compare those distributions using the Kolmogorov-Smirnov. Because it has the capability to test a ton of different distributions, we obviously lose something when we test it. So sometimes the Kolmogorov-Smirnov does not detect deviations from any particular distribution. So you can do a Lilliefloor's correction, and that's going to really assist the Kolmogorov-Smirnov in being similar to the Shapiro-Wilk in terms of powerfulness. All right, so you run a test of normality in SPSS, and here is some results. So when you look at the significance column, we're looking at, right, the alpha of 0.05 is our cutoff point, so anything less than that is significant. So both tests say that both the percentage on the SPSS exam and numeracy are both significant deviations from normality. Degrees of freedom kind of gives us a hint as to what the sample size is. So we have some fairly large samples here, which may say, all right, well, the tests are not very accurate when it gets to very large samples, so maybe we do have normal data here, even though the tests say we don't. So in that case, what do? Go ahead and look at the graphs. And now if you want to compare groups, there's two ways you can do that. You can look at the entire sample together, or you can look at the normality for each group. If you look at the entire sample, it is very likely that you are not going to get normal data. But that doesn't matter, because if you're comparing groups with each other, it's more important that each group is normal and not the entire sample together. All right, next one is homogeneous variances. This just says that we have equal variances or similar variances. There's three ways that we can look at this. There's graphs, but we usually only use that for correlational data. What we usually do is run the Levene's test. So now you said, okay, so you said you didn't want to run too many tests when it comes to the data, because of that would really bias future statistical tests. Most of the tests that are run in SPSS already automatically do the Levene's test, which means it's automatically correcting that factor for you. So you're still looking at an alpha of 0.05 because SPSS is fixing the problem for you. So that is the one good thing about the Levene's test, is it's already helping you out if you use SPSS. And then the other test is you can just simply look at the variance ratio. All right, so if we look at the graphs, the little horizontal lines that are in these graphs right there, that's the mean for any particular data set. And then what we do is we connect the means with a trend line. And what we want is we want all of the means to be very close together, all the data points to be very close together, right? What we don't want is a huge spread. The huge spread means that our variances are not equal. All right, the Levene's test, just like every other null hypothesis, the null hypothesis says that the variance of one is equal to the variance of the other, or variance 1 minus variance of 2 is equal to 0. Either way, they mean the same thing. It's actually going to conduct a one-way analysis of variance. I know we haven't talked about that yet, but the only thing you need to know at this point, what is the Levene's test, what is it testing, and how do we interpret the output? So, problem with Levene's test, because there's a problem with everything. Very, very large sample sizes that have very small differences will produce a significant result. So let's look at one of the outputs here. We've got the two data points, and you can run the variance test, the homogeneity of variances, based upon various elements. So you can run it on the mean, the median, and the trimmed mean. Most of the time, unless we're trying to fix a data set, we're really just looking based upon the mean. So if we do that, 0.05 is our limit. So the percentage on SPSS exam is greater than 0.05, so the variances are homogeneous. For numeracy, we have 0.008, that is less than 0.05, which means we do not have homogeneous variances, we have heterogeneous variances. All right, so what happens if we have this really, really large data set and we're still getting significant differences? We can run, it's either called the Hartley's or the Box's F-max test, where we're taking the ratio of the larger variance divided by the smaller variance, and you're comparing that to the square root of 3. And if the larger variance divided by the smaller variance is less than the square root of 3, then it's really not biased enough to bias the test, right? So larger variance divided by the smaller variance has to be less than 3. Hartley does something a little bit slightly different. It depends upon how many variances you're comparing, what your degrees of freedom are. Degrees of freedom are your x-axis, and what critical value you're looking at. So the problem I have with this is you have to find this graph every time you want to be able to figure this out. At least Box's test, square root of 3, pretty easy to remember. All right, correcting problems in the data. So now we don't have normal data. What are we doing? Well, if we don't have normal data, we probably have some outliers somewhere. So you can do one of 3 things. You can just simply remove the data point. You can transform the data, or you can just change the data point altogether. Well, let's talk about removing the data point. You better not remove that data point unless you have a very good rationale as to why you're doing that. Otherwise, you can be accused of fudging an entire data set. So a good example is I collected traffic data from 4 to 5 p.m. And the outlier that I have was my last data point I collected. I thought the peak hour was from 4 to 5. And that last data point just doesn't seem to fit. So maybe my peak hour assumption was wrong, and that last data point was actually falling into the off-peak hour. Okay, that would be rational, and that would be a good reason to remove that data point. Changing the data point, we'll talk about that too. It's also not advisable unless you have a pretty darn good reason why you want to do that, why you have to do that. To transform the data, there's 3 different transformations you can do, and SPSS will do this for you. You just have to create the equation to do that. So the log, the square root, and the reciprocal. Here's a good example of what can happen to your data set. So we have a before, and we've got some pretty nice skewed data. Once we transform that data, we've got some really fairly decent normal data. The skew is obviously removed. Looks a little bit better. There's still a little bit of a skew there, but it's not nearly as bad as it was before. The square root, again, we've got a skew. And after the skew, it looks like it is completely removed. And the reciprocal, again, we have a skew. And after the skew is removed, but clearly, when you look at the 3 options, it looks like the square root transformation is the best of the 3, and so that is the one that we would choose to proceed with. Sometimes, if you transform your data, you might say, well, I don't like this because this is not normal, and I would like a little bit better normality. Well, you transform your data and you've messed it up. So it's better just to stick with the original data set. Now that data point that you don't like, that you want to change, the only reason you should change it is because it's unrepresented and it's biasing the model. What can you do? Well, you can say, well, what's my next highest data point? And I just add 1 to it. You can convert it back from a z-score. So if you have a z-score of a 3.29, you can say, all right, 3.29 is an outlier. I want to reduce that back to within 3 standard deviations. So I'm going to use my z-value of 3. And then you can come up with a new number. Or you could replace that data point with a mean plus 2 standard deviations. So now it's a little bit more normal than the 3 standard deviations. But again, you have to have a very good rationale as to why you're going to be doing that. All right, what else can you do? No matter what you do not have normal data. Well, don't use a test that requires that assumption. Or there's some other options. There is the trimmed mean, where you can take, you could do a 5% trimmed mean, a 2% trimmed mean. 2% trimmed mean means you take the top 1% on the low end and the 1% on the high end, and you remove them from your data set. And then there's some other bootstrapping methods where you're taking your distribution and you can generate new data from that distribution and add that to your data set. I'm not a big fan of bootstrapping. Trimmed mean I'm somewhat okay with, but usually I just don't use the test that requires that assumption if we're having an issue, because I really don't like changing my data set